Okay, so recording has started. So welcome everybody to the next lecture of PhD training in data science. And today we are continuing the trend of dealing very simple things in statistics, because statistics is seen as the very basic of data science, as well as machine learning. Many machine learning methods essentially stem from statistical methods. And big data naturally requires lots of statistics. So we still continue with the basics. But today's goal, well, is firstly to see how our common sense knowledge can be strange at times, but also try to see how mathematical exploration and scientific thinking could help to deal with that. And last time, we've ended with a simple homework question. I've asked to try to okay, so just a moment. I'll open another one. Okay, that's the one. Oh, wait, I still can use the chat function if I do it in this way. Okay, perfect. So now we have everything. Yeah, so we had a simple exercise. We wanted to test this claim. If all numbers are positive, then a sample mean, which is often denoted by the bar at the top, is also positive. And that was a homework to test yourself and trying to prove it in a strict way. And I don't want to spend much time on that. So I will just reveal one of the possible solutions or proof possibilities. So one of the options to do it this way, but again, you're welcome to try yourself on that. So similarly, if we know by now from our personal experience probably that if the average mark on the exam is 60, it doesn't always mean that all students have passed the exam, unfortunately. And then the next question, if you want to explore things further, is what should be an average mark to guarantee all passes? Well, you're welcome to type your question in the chat, but actually I would like us to maybe consider it as another homework question. So I'll leave it for now. Just think about it. What should be an average mark so that you can, well, yes, 100, it's a nice one, but maybe something smaller will fit, because 100 is indeed will guarantee all passes. That's true. But I wonder if anything smaller will suit as well. Just think about that. But let's move to the next one. So we've seen that the average is a nice measurement, but unfortunately it's not enough, because if you don't know the bounds, the average can be the same for -1, minus 1,000 and plus 1,000, and -1 and 1, they will have exactly the same average. And also, I think I've mentioned the problem of the mean is its sensitivity to outliers. So if Elon Musk will join us in this session out of a sudden, just by his presence, he will make us all very rich on average, just by being an outlier. That's why another descriptive value is needed. And the simplest one is to measure the range. And the range, by definition, is just the interval from the minimum to the maximum value. So what is the range of our usual real-life question about the mean livable temperatures? What is the range in this case? You're welcome to answer in chat or live. It's a very simple question just to check that we are all following. So what is the range? Yeah, very good. And very good. So the range indeed can be defined in different ways. That's why if we say that it's just an interval from minimum to the maximum, then the answer is from 5 to 17. But sometimes the range is measured as just one number, and then obviously it will be 12. So both answers are very good. Well done. Thank you. Now, it is possible to measure similar thing, but in terms of how far everything is from the mean. That is what is the amount of variation of our data, not just the range, but the variation of our data from the mean. It's also called variation, dispersion, or residue by different names, but the essence is the same. So one of the obvious ideas will be this. Just take all possible deviations from the mean and then just take the average of them. Is it a good idea? What do you think? So just taking the average of all deviations from the mean. What will happen if we take just the average of all deviations from the mean? Well, maybe thinking about a simple example might help. So what will happen if we take the very simple set consisting of two values, -1 and 1, and take the average of deviations from the mean just for this set? What will be the average of all deviations? So what is the mean in this particular case? The set consists of -1 and 1. The mean is equal to, obviously, 0. And the deviations from the mean will be -1 minus 0 and 1 minus 0. What will be the average of those numbers? Well, I hope we all see that -1 plus 1 will cancel out. And the question is it just happened? Is it a unique case because I took the numbers like that? But we can understand that, well, actually, no. By the definition of the sample mean, it's in the middle of our data set, which means that if we indeed take the deviations in the way that I've suggested, just take the differences between the numbers and then try to take the average, well, even before we take the average, when we just sum them up, they will always give us 0, which means that just taking the deviations of the mean is not very meaningful. Well, and there are some calculations as well. Yes, great. So the idea is to take power 2. That's a good idea. Why? Well, because then the main problem here is that the signs get in the way. We go one way direction and then we go into another direction, which means that the signs of differences or deviations will be different, and we would like to get rid of the signs, right? So thank you very much, Marjan. That's indeed a way to go. Try to get rid of the signs. But probably the best or the first attempt to get rid of the sign is to take absolute value. But probably we also know that indeed squaring is used universally. But why? Why do you think? Oh, surely, yeah. So why do we square? Because indeed it will be much easier just to take the absolute value. why bothering with taking the power of 2? Because absolute value is just taking the distances, so taking absolute value would suffice. Why bothering with squaring? Because you see, when we square things, we will naturally obtain a larger value of distance than if we just take the distance. But we know from school that we indeed do use squaring. The question is why? Any ideas why? Why do we take power of 2 instead of just taking an absolute value? Okay, no replies so far. So the main problem is that we would like to use some complicated formulas. The outliers are given a grade in weighting. Isn't a good thing actually, because yes, if you would like to have a larger, huger weight to outliers, yeah, I like your idea, Adam, because then indeed outliers will have a huge weight. But we also know that we sort of negate this weight, or try to negate it, by taking a square root later. Yes? So the natural question is, why bothering? Why taking a second power only then to sort of negate this effect by taking a square root? A bit silly, isn't it? And for my personal understanding is that it's because we would like to use this formula later. And not simply use it, but use it in mathematical formulas. And in many formulas, we would like to see the changes that are happening with time. And if you are looking at changes with time, we are looking at dynamics. And if we are looking at dynamics, that means that we would like to be able to do differentiation. And as we know, as you can see, the function of absolute value is not differentiable at 0. And that's quite often where we are mostly interested in. And that's quite an interesting example, because in school, for example, we all learn that derivatives are defined by simple formulas, and we can easily find derivatives of everything. Well, that is of linear functions. Whilst in fact, derivatives are not as easy as you might think. And such an obvious thing as some kind of step in one point, or a corner in one point, it breaks the whole derivative or differentiation mechanisms quite badly. So differentiation is not as easy as just applying formulas. It requires quite a lot of checking behind it, quite a lot of assumptions behind it. And one of the easiest, or one of the main assumptions, is some kind of smoothness around everything. And to obtain that smoothness around the 0 point, indeed, the easiest way will be to take some kind of positive power. And the smallest positive power will be 2. And indeed, outliers are given a greater weight like that. And it's not always a very good thing, because indeed we take a square root later to sort of slightly make it less noticeable. That's why the smallest even power is taken, not the 4th, not the 6th, but the 2nd. Okay, and that's quite an interesting thing in itself, which is not always thought about. And by the way, it's resurfaced later when we do something like least squares approximation. That's why indeed we use squares instead of absolute values. But sometimes absolute value approximation is also used, but then it has a different pitfalls behind it. Okay, so that's why indeed we define the sample variance like that. We take all the deviations, then square them, and only after that we take the average. And also we introduce standard deviation as square root of variance, mostly to get rid of the impact of the square and to make at least units as they were before. to make this difference of squaring slightly smaller. I think it's a very well-known formula. Any questions about this formula? Do we all know it from school? Or is there anything strange in this very well-known formula? Something that probably didn't have in school. There is one small detail which might be slightly unfamiliar. No, nothing noticeable? Okay, so if you are just taking the average of those squares, just a simple average, and we have n deviations, what should we divide by? So we sum them up, all n values, from the first one to the nth one, and then to take a simple average, what should be divided by? And for a simple normal average, we should divide it by n. Yes, thank you very much, absolutely. But in this case, it's n minus 1. And it's not a misprint in this particular case. It's so-called Bessel's correction. And here, effectively, a magic thing happens. We are moving or shifting from a simple descriptive statistics to inferential statistics. So what's going on in here? Actually, we are dealing with samples, whilst our main goal is to do some kind of inferences about the whole population. So if we were able to indeed measure absolutely everything in the population, then the formula will be like we assumed it to be. That is the pure and simple arithmetic average of squared deviations. But we are dealing with a sample because we are dealing with big data, and our sample is always smaller than the whole population, which means that we need to divide by n minus 1 to reduce bias. So why this bias appear in the first place? Well, firstly, how it was noticed. It was noticed by an experiment because, well, developing some kind of theory or method is nice, but being able to test it on a synthetic data is quite useful. And you can imagine, suppose you have created a synthetic population and you know your ideal mean and a standard deviation or variance for the synthetic population. And then you want to test what's going on if you take samples from that big population and calculate variance and standard deviation based on those samples. So what do you think will happen to the variance if you are taking the samples instead of the whole population? Will their variance be smaller, larger, equal? Can we try to understand what will happen to the variance? So if you take not the whole population, but some kind of sample, a finite sample which is smaller than the whole set, the whole population, what will happen to the variance? Or even what will happen to the range to start with? Well, we can imagine that the population is always larger, the sample is always smaller, which means the variance will always be also not larger, smaller or equal. And in most cases, probably it will be smaller just because we don't have all the samples, the whole range of things to measure. And that's indeed what is happening, which means that the variance or standard deviation obtained in this way from samples will always be smaller, and an attempt to slightly increase it, the cheapest attempt, will be divided by n minus 1 instead of dividing by n. But actually it turns out that there is a more complicated science or proof behind it. So what happens if we first find the sample mean and then take all the deviations? As we found out, the sum of all deviations is always equal to 0 if we do not square them first or don't take the absolute values, just the deviations themselves. So that's the rule which appears just from the formula of the mean, which means that this equation, equality to 0, gives us an equation which in fact reduces the degrees of freedom, because one of the variables, one of the deviations, can always be represented through the rest, which means that the number of independent deviations will be not n anymore, but one less, n minus 1. And it turns out that Bessel's correction indeed takes into account not n, but n minus 1 values and gives unbiased variance. And you are more than welcome to look for more explanations and very nice examples on the Wikipedia page, because it has updated since I last looked at it 3 years ago, and now it contains very nice examples, numeric examples as well. So that's what Bessel's correction is for. Bessel's correction corrects variance and gives unbiased variance. The question is what it does to standard deviation, and the answer is, well, actually it doesn't correct the bias in standard deviation completely, which means that for standard deviation sometimes other types of denominators are used. Usually it depends on distribution, but we are not using them, and just for simplicity we will stick to n minus 1 in the denominator. But keep that in mind if you're using some kind of statistical program or machine learning program. Sometimes it makes sense to check how exactly your standard deviation, which we all know from school, how exactly your deviation is computed. Okay, right. Any questions here? So again, that appears because we are now dealing with kind of inferential statistics when we try to make some kind of inferences about the whole population with well-known data about samples, well-known measurements about samples. Well, another way of measuring things is percentiles, and that's just a reminder that percentiles, quartiles, is a particular case of percentiles, and they separate the data into some kind of parts, quartiles into 4 parts, percentiles into, well, similarly 100 parts. Well, the second quartile is actually has its own name. So the second quartile separates the data into exactly 2 parts. So do we know the name of the second quartile? So the second quartile is something that separates the lowest half of 50% of the data from the highest half of the data. Yes, absolutely. That's called a median. Very good. It's in the middle. Well, that's the full definition. So let's try to see what are the quartiles in this data sample. So can we try to compute quickly the quartiles? So if we are separating the data set into 4 parts, then it's done by 3 points. Yeah, and the quartiles are here. You're welcome to check your calculations. That's just a reminder. Okay, good. But let's try to check our understanding on a very particular real-life problem. And I suggest us try to apply our knowledge to real-life studies which is now known as Dunning-Kruger effect. It was published in year 2000 in the paper which is named in front of you, Unskilled and Unaware of It. So there were four quite large studies with different tests, and the participants were scored on those tests, but also they were asked to grade themselves or predict their grades for those tests. And the result was quite overwhelming. The participants who scored in the 12th percentile, which means quite low in the range, they always overestimated their performance, and like universally predicted their abilities to be on the 62nd percentile, so quite a bit higher. But also what happens to the top performers? Top performers tended to underestimate their competence because they thought the tasks that were easy for them were easy to everybody else. And that universal sort of rule has been confirmed in many other settings. And in general, it can be represented by saying that Dunning-Kruger effect is about people who know not enough to understand that there exists knowledge outside of what they know. So there exists some knowledge they don't know yet. So that sort of effect of a huge confidence. And it was at the time quite a big discovery, which had quite a substantial media coverage. And one of the well-known newspapers presented results in this way. So they said that 68 professors rated themselves in the top 25 for teaching ability, and 90% rated themselves above average, despite this being mathematically impossible. Quite catchy, right? But now let's think, and let's try to apply some kind of critical evaluation of this particular media coverage. In the statements above, which part is mathematically impossible? So, for example, the first part, that one, is it mathematically impossible? And if it is, why? It's very catchy and very sort of obvious, isn't it? So let's try to think about it. So is it possible to have 68% high flyers that grade themselves in the top 25? So is it possible? Is there any mathematical impossibility in the first place? Well, it's a silly question, isn't it? It's sort of obvious. But let's try to read what it's written in front of us in some more detail. Well, firstly, it's not exactly clear how we should read the top 25%, because if it's just top 25% of grades, then surely everybody can give themselves any grade they want, and it's perfectly possible that all 100% will give themselves 99 mark, and no contradiction in it at all. But another interpretation is a bit more interesting, is when we arrange everybody for teaching ability and then take top 25% for teaching ability, or top 25% of people. So what happens then? This means that we can revert the initial problem in a more precise way. So rewording will be like that. Does there exist a ranking system of teaching abilities so that 68% are in top 25%. Well, in that case, we are comparing the same thing with the same thing. And then we can simply use maths. And 68 is larger than 25, which means that such ranking indeed does not exist. So you see, it was all trivial, but very much depending on exact wording. Any questions here? Okay, so let's move to the second part. And the second part was about the averages, and reworded, it sounds like that. Does there exist such a ranking of professors that 90% of them are ranked above the average? So let's deal just with the ranking. What do you think? Can we vote yes, no? What do you think? Does there exist such a ranking? So can you please put in the chat just simple yes or no? What do you think? So does there exist a ranking such that 90% are ranked above the average? What do you think? Does there exist? Does not it exist? No, just a simple yes, no voting, and then we'll see where it goes. I'm not even asking for some kind of examples. Okay, thank you very much, Daniel. So any more votes? Yes, another no. Thank you very much. Any more votes? Okay, come on. Let's take the number of votes to at least 5. So we have 2 votes so far. Can we have 3 more? Great. Another no. Yes, 1 more no. So how many? 1, 2, 3, 4. 4 no's. Very good. 1 more vote. Or just throw a coin and or support the majority. Okay, probably everybody else is asleep. Okay, so let's move on. So let's try to do a simple mathematical problem in a very simple numerical terms. And the problem is like that. Can we give an example of 10 values such that all except 1 are greater or larger than mean? So 10 values so that 9 of them are larger than sample mean and 1 is smaller than the sample mean. So for example, if you take 9 of them, yes, very good. So 9 are 10 and 1 is 1, 9, 10 and yeah. And the usual attempt is to take the smallest possible numbers. Thank you very much for your answers. So one of the examples is to take 9 of them equal to 1 and then outweigh all them by some kind of large negative number. Then surely we'll see that 1 is negative and average is 0. And then this holds. Okay, and we can think that probably that's an example to the problem that we have. There is theoretically no mathematical impossibility in the statement that 90% can be above average. That's exactly what happens in front of our eyes, right? But now let's think. So what we dealt with was a large negative number. So the obvious question is, what will happen if we restrict ourselves to the interval from 0 to 10? But actually, your examples are answering that question already. It is also possible to give such an example in this case as well. Yeah. So 9 are equal to 1, and 1 is equal to 0. Then the same thing happens that 9 of them, or 90%, are above average, and just one bad apple spoils everything, spoils the barrel. Which means, again, that that's another possible solution. And does it give the answer to the mathematical impossibility problem? What do you think? So we've demonstrated that it is possible to have all numbers greater than the mean except of 1. It is possible to have 90% larger than the mean if 10% spoils everything. Yeah? Which means that the answer should be that it's mathematically possible, right? Well, actually, we've outlooked one more restriction. So it is possible to have 10 positive values restricted to an interval so that 90% are above average. But in marks, there was one more restriction. Can anyone guess what restriction we missed so far? Okay, so let's try this problem. Does there exist a sample of 10 integer values in some interval? Well, let's take this interval from -5 to 5 to make the things more striking, such that all except one of them are positive, but the sample mean is not positive. So you see the main difference with the previous problem is integers. Does it make a difference? So can we give an example of 10 integer values with a very similar properties? Tricky, isn't it? Y minus 5, there are 4 of them, aren't they? And we need 10 integer numbers. So we need 10 integer numbers from the interval. Yeah, that's a good attempt. Why is it good? We'll see in a moment. But can anyone have a sample of 10 integers? Tricky, isn't it? So we practically are trying to check different numbers. Yes, 0 is neither positive or negative. Not positive, which means that one of them, positive means strictly larger than 0. That's why the sample mean is not positive, means that the sample mean can be either smaller or equal to 0. And positive indeed means exactly larger than 0. Yeah, it's tricky, isn't it? Cannot find such sample, which, well, does it mean that it doesn't exist? And that's a common problem, isn't it? Sometimes we try and try hard, but cannot find something. Does it mean that we've proven the things? Well, not always. It can be a good proof that I tried everything but wasn't able to find it if we can exhaust all possibilities. But in general case, it is enough to give just one sample as a counterexample to disprove things. But no amount of examples is enough to prove the statement. And that's why it's possible to use some other ways of proving things. So let's try in our particular case. Cannot find such a sample. Does it mean that it doesn't exist? Well, actually, yes, because there's no such sample. How to prove it? So, by contradiction. Suppose that such a sample exists. Suppose that we have such integers. And suppose only one of them is not positive, which means that smaller or equal to 0. Now we are dealing with integers, which means that it's reasonable to try the smallest positive integer, which is 1. What will be the mean then? Well, the mean will be our unknown a1 plus all other ones, which means that it will be equal to a1, which we don't know yet, which should be non-positive, divided by 10. We have 10 values, plus 9 over 10. But now remember, we are restricted on the interval from -5 to 5, which means that the smallest integer that we can take, or the smallest number at all, is -5. And if we take -5, then the sum will be equal to 4 over 10. So the mean will always be positive, which contradicts the assumption that our mean should be non-positive, which means that from contradiction, we've proved that indeed this example does not exist. So the integers is indeed a game changer in many, many, many situations. And what we did for a continuous case is not always true if we restrict ourselves to integers or just to some discrete number of cases. That's a very good example. Well, okay, so we've done everything, but then the question is like that: is it always the case? Can we not find such a distribution of 90 to 10 at all if dealing with integers? And then the next question: what biggest number of integers in this interval can we take such that all are positive, but the sample mean isn't positive? So here, in the previous case, the problem was that we had too many integers in a sample. So the question is, what is the largest possible sample that we will be able to find such an example? What do you think? What is the biggest possible number? Any suggestions? Okay, so let's try to look at it together. So similar, let's try to repeat the steps that we've used in the previous case, but with number n instead of 10. Okay, so let's repeat the calculations. What will happen then? So, as before, let's write them down. And suppose that A1 will be our negative that will try to outweigh the rest. And all the other n-1 will take the smallest possible integer equal to 1. Then we'll have this formula for the sample mean. And then if we write it down, then we need that number A1 plus n-1 divided by n. We want that to be non-positive. So again, remember that the smallest number, negative number from the interval from -5 to 5 to outweigh everything is -5. So let's just set A1 equal to -5 and see what's going on. So what is n in this case? So what will be n if we set? Yeah, very good, absolutely. So just let's put -5 into the equation, and then indeed n is the largest number. Well, it's very useful to check that this number, which was obtained from theory, is indeed realizable. Well, that's also easy. If we set them as 1 and -5, then indeed we'll have everything we wanted. Any questions? Now we can go back to our initial newspaper question. And we can say that mathematical possibility depends very much on the way how the measurements were done. Was it a discrete scale or was it a continuous scale? And such scale for ranking is, or for measuring, is known as Likert scale. And quite often in sociological research, the discrete scale is used. And as we've seen, that can make a huge difference. Using discrete case of integer numbers is not the same as using continuous scale with all possible numbers in between. And then if the discrete scale is used, the answer depends on a sample size as well. So you see, mathematical apparatus with simple numbers and doing some exploration around it allows us to see the processes behind seemingly obvious common sense and allow us to evaluate it properly. Right, but let's move further and consider all possible, or just remind ourselves of several possible ways to evaluate point estimate. So also mode is used quite often, and it's the most frequent value. So let's compare all those three numbers. So the question is the median is always equal to the mean? What do we think? So the median, it's the middle of the sample. We've covered that already when finding percentiles. So what do you think? Is the median always equal to the sample mean? Very good for Gaussian distribution, yes. So actually, thank you, Tim, because you are sort of going ahead to my next question. So here, the question was for any data sample. For Gaussian distribution, it's indeed yes. But for any data sample, if it's not Gaussian, is the median equal to the mean? Well, yes, no, it isn't, because yes, we can give a simple example. So to disprove something or to answer this kind of questions, that's indeed enough to give just one example. But then the next question, when are they equal? And yes, one of the answers we've got already. So for Gaussian distribution, they are equal. So when are they equal? So one of the attempts, so what is so beautiful in Gaussian distribution is that it is symmetric. And indeed, if a sample is symmetric, which means that everything is symmetric around the mean, then median and mean are equal. And the question is it the full description? Are median and mean equal only for symmetric distributions? What do you think? Are median and mean equal to only for symmetric distributions? Well, and again, one example would have been enough. So for example, this data sample, it's not obviously symmetric, but the mean is equal to the median. And to see what's going on and to see what when distribution is symmetric, quite often we look at some pictures, and one of the common pictures in statistics is histograms. Now that's just the plots that depicts a number of observations that falls into each of the categories or bins. It looks like that. For example, in my example, the histogram was this, and we can immediately see that it's not really symmetric. And histograms are very good to trace shapes and see what is symmetric and what is not. So here are some examples of them. For example, the first distribution is obviously symmetric. The last one can be also called symmetric, then skewed right, skewed left, bimodal, multimodal. And you see that, well, how about the last one? Does it really look symmetric to us? Well, I don't know. That's a personal preference. And it turns out that it comes from history. Historically, there was a definition of symmetric, which was formulated from median and mean. But nowadays, being symmetric is judged by the shape of the distribution. And from here, actually, we're getting a common misunderstanding about skewedness and central tendencies. So we usually learn from statistics course, statistics module, that in symmetric distribution, indeed mean, median, mode, they coincide. If you have negative skew, then we learn that mean, median, and mode are in this order. And in positive skew, mean is always to the left of the median, right? It sort of is diverted towards the outlier. That's how we learn it. And that's, in fact, is an artifact of an old historic definition of skewedness. Because, believe it or not, some time ago, indeed, skewedness was defined like that. So the definition was that the positive skew happens if the mean is to the right of the median. Not anymore, because now the shape of the distribution is defined from the plot, from the graph, from visual representation of that, which means that it's not always the case. And in fact, this general rule is, well, very, very frequently violated for real-life data. In particular, when the tail is very long, but another one is sort of compensates that by a fat tail. Well, and a very simple example of a smallest distribution I can think of is this one. It does not conform to that rule which you see in front of you. And in real life data, fat tails distributions are very common, especially in finances. So that's just another example of a textbook rule which is violated more often than not. Okay, so let's just quickly cover some other I don't think I will have time to cover, but I don't want to spend much more time. So I think I'll just go through them. So what are the main properties? The mean does not always belong to the sample. And I think we all understand that from trying to find a mean person with a mean number of legs. That one, we've covered that. The median. And that very much depends on how we decide it. If you just simply take the middle of the data, then sometimes it belongs to the sample, sometimes not. But the mode, by definition, always belongs to the sample. So there's a comparative table to compare all of them. And I think the slides will be posted, so you can have a look at them. So the main outcome of everything is that the more the merrier, the more descriptors we have, the better. And some of the descriptors are suitable for different tasks. For example, that's real life data from baseball salaries. And depending on a question, you might be interested in different values. So the mode is relatively small, and that's exactly the number that one might expect if they just start their career in this business. The median is the median salary that you might expect to get if you are long enough in that business. But also, if you would like to see if there are huge outliers or rich people or best players, then the mean can be quite useful. And it is also useful for in economics in evaluation of financial taxes or things like that. So what mean can we get from this picture? So each of them are useful in their own sense, and also means are useful in real life. For example, famous Chicago jury project measured decisions reached by professional judges and juries. And it turns out that in almost 90% of all cases, the same outcome was reached by them, which means that averages can be quite useful in real life despite all their drawbacks. And also, please remember that there are different types of means, and if dealing with some kind of especially method, be careful with what kind of mean is meant behind it. Quite recently, I faced two different models which consistently produce different results just because one was based on arithmetic mean and another one was based on geometric mean. So please remember that the word mean has different meanings. Okay, I will skip the next problem. So just a summary. We have several descriptors and all of them are useful, including histograms, standard deviations, Bessel's collection, and other types, but the results of everything depend on exact definitions. And that's what we'll devote our next lecture to. The next lecture will be devoted to exact definition of probability and Kolmogorov axioms that allow us to give those. For today, I think that's all. And that's just a small cartoon to, again, envisage the importance of meaning of numbers behind everything. Any questions? Okay, I'll stop recording.